All right, let's jump right in. We're about to talk about what is, no exaggeration, probably the single most important invention of the 20th century. I mean, this is the fundamental building block of, well, everything in our digital world. It's a tiny, tiny component, and there are so many of them, it's almost impossible to wrap your head around. 100 billion. And no, that is not just some random huge number I pulled out of thin air. That's roughly how many transistors we can now cram onto a single top-of-the-line computer chip. I mean, think about that. You've got more of these little switches on the tip of your finger than there are people on the entire planet. And that insane density is exactly why your phone can do what it does, why we can have supercomputers modeling our climate. Okay, so what is a transistor, anyway? It's a fair question, right? We hear the word thrown around all the time, but what is this tiny little marvel actually doing? How does it power literally everything? All right, let's break it down. We're going to cut through all the complex jargon, because at its heart, a transistor is actually surprisingly simple. It all boils down to one core idea. Yep, that's it. At the end of the day, it's just a switch. But it's an incredibly tiny electrically controlled switch with 0 moving parts. And it can flick on and off billions of times every single second. When you put billions of those together, well, that's how you can do any calculation you can possibly imagine. They're basically the microscopic brain cells inside every single electronic device you own. So how does this tiny electrical switch actually, work? To really get it, let's use an analogy that makes it super clear. For just a minute, I want you to forget all about electricity and just picture a simple water faucet in your kitchen. Okay, look at how perfectly this maps out. In our transistor, you've got something called the source. Think of that as the main water pipe coming into your house. Then you've got the drain, which is just like the spout of the faucet. And here's the most important part, the gate. The gate is the handle. A tiny little bit of effort on the handle, the gate, controls this huge flow of electrons, which is our water, going from the source to the drain. Simple, right? So here's the slightly more formal definition for the most common type of transistor, the MOS transistor. And you can see the parts we just talked about: gate, source, drain. There's that fourth part, the body. But you can just think of that as the foundation the whole thing is built on. But the key thing to remember, the big takeaway, is right there. A voltage on the gate is what controls the current. Handle controls the water. Okay, so here's where the magic really happens. When you apply a positive voltage to the gate, you turn the handle, it creates this conductive little path, this channel, in the silicon right underneath it. Suddenly, you have an open pipe, and boom, electrons rush from the source to the drain. The switch is on. Take away that voltage, turn the handle back, and poof, the channel disappears, the flow stops, the switch is off. It's really that simple. Okay, that's how it works. But how in the world do you build a switch that's measured in nanometers? Well, it all starts with one of the most common elements on our planet. That element is silicon. And the reason we use silicon is because it's what's called a semiconductor. It's a great name because it's not a great conductor like copper, but it's not a great insulator like rubber either. It's right there in the middle. And that in-between property means we can tweak it and control it really, really precisely. But here's the thing. Pure silicon on its own isn't actually that useful. This is where the real genius, the real secret sauce of making transistors comes in. The trick is to intentionally make the silicon impure. We have to contaminate it, but in an unbelievably precise and controlled way. And this process has a name. It's called doping. What we do is we sprinkle in just the right amount of atoms of other elements, things like phosphorus or boron. And by doing that, we can create specific zones in the silicon that either have too many electrons or not enough. So picture it like making a sandwich. We start with our main slice of silicon, which we call P-type. You can think of P for positive. It's kind of hungry for electrons. Then we infuse 2 spots with an N-type impurity, N for negative. These spots now have a surplus of electrons, and those 2 spots, they become our source and our drain. So what you've got at the end is this NPN sandwich with that electron-hungry P-type material squished right in the middle. And this setup is just brilliant because it automatically creates the off state. You see, wherever those N-type and P-type regions touch, a natural barrier forms. It's like a wall that just stops any electrons from flowing. The whole job of the gate, then, is to apply that voltage to temporarily tear down that wall, to create that channel right through the middle and flip the switch to on. Okay, so for decades, the name of the game in the tech world has been Moore's Law. It's simple. Make transistors smaller and computers get faster and cheaper.
Easy, right? Well, not anymore. As we get down to the atomic scale, making things smaller is starting to cause some very big problems. The problem has a name: short channel effects. Basically, when the distance between the source and the drain, that channel we talked about, gets just ridiculously short, the transistor stops acting like a nice clean switch. The drain, with its own powerful electrical pull, starts to interfere and basically overpower what the gate is trying to do. Let's go right back to our trusty faucet analogy to understand this. The first problem is called subthreshold leakage. This is literally a leaky faucet. It's supposed to be off, but it's constantly dripping electrons, just wasting power. Then there's something called DIBL. This is wild. It's like the water pressure coming out of the spout is so strong that it's actually helping to force the handle open by itself. It makes it really hard to keep the switch off. And finally, there's parasitic capacitance. This is like the whole system gets kind of waterlogged. The pipes get sticky and it just gets sluggish and slow to turn on and off. So what's the bottom line here? The crucial takeaway here is that as we keep shrinking these transistors, they're actually getting less efficient. They're leaking electricity, burning power even when they're supposed to be off, and they're getting slower to switch. This is, without a doubt, the single biggest challenge facing engineers in this field today. And that brings us right to the cutting edge of semiconductor physics. The big question is, how do we keep this incredible party going? How do we maintain the progress of the last half-century now that we're slamming up against the hard physical limits of our materials? This quote here just sums up the eternal problem perfectly. It's a constant trade-off. See, to make a transistor switch faster, you want to lower its electrical resistance. Makes sense, right? But the very things you do to lower the resistance often end up increasing something else called capacitance, which, you guessed it, makes it slower. It's this constant push and pull, this never-ending battle to find that perfect engineering sweet spot. And so that leaves us with the big one, the ultimate question. We've pushed silicon about as far as it can possibly go. So, what's next? Are we looking at totally new materials, like carbon nanotubes? Or completely different ways of building these things? We don't know for sure, but one thing is certain. The hunt for a better, faster, smaller switch is the quest that will drive all of our technology into the future.